Hello, everyone, and thank you for joining us today. We hope you are staying safe, and we appreciate you choosing to spend the next 45 minutes or so with us. This is part 5 in a series of algorithms, a series of webinars called Using Graph Algorithms for Advanced Analytics. And I'm sorry to say that it's the last in the series. I've thoroughly enjoyed listening to the prior 4 episodes, and if for those people on the call or on the Zoom session who did have the opportunity to listen to any of the prior webinars in the series, I'm sure you'll agree with me that it has been excellent, and I'm very excited to see what Victor Lee has in store for us today. And I'm delighted to introduce Dr. Victor Lee. He is Head of Product Strategy and Developer Relations at Tigergraph, and has a bachelor's degree in electrical engineering and computer science from UC Berkeley, and a master's degree in electrical engineering from Stanford University. So I'm sure you'll agree with me that he has a very illustrious background. Moreover, he has a PhD in computer science from Kent State University, where he focused on graph data mining. He has over 20 years in the tech industry, and if I'm not mistaken, closing in on 6 years at Tigergraph. He has played a pivotal role in developing the company that we know, Tigergraph, and I'm excited to introduce him. And before we get started, some housekeeping issues. Your phones are muted, but that is not a sign that we do not want to hear from you. Quite the contrary, we encourage you to submit your questions in order for this webinar to be interactive and informative, and that way we can help shape the webinar when we see your questions. So please submit them using the Q&A tab in the Zoom panel. The webinar is being recorded and will be uploaded to our website shortly. We're very good about getting the webinar up on our website within 2 or 3 hours. And we'll also email you a link to the webinar along with any other materials that Victor wants to include, the slides and other items. So look for that email shortly after the webinar finishes. Last but not least, if you have any issues with Zoom, they're becoming very rare these days, but if you have any issues with Zoom, please contact us via chat and we'll do our very best to resolve them in a timely manner. And with that, I am delighted to hand the webinar over to Victor.
Thank you, David. So yes, I have also very much enjoyed being able to present this series of webinars for you. Every time I take a good look at another topic, particularly when you're preparing to teach something, you tend to discover something new. So I've actually learned more about these topics that I thought I knew pretty well, but I'm having some new insights. And so it's been a great experience for me. So we're going to do a little bit of recap of what we've done so far getting to here. Then we're going to turn to our topic for today, classification algorithms for graphs. Start by talking about some use cases and then looking at how they work, what is a classifier, and then the idea that in many cases you actually want to train a classifier. We're going to focus on the one called the k-nearest neighbor algorithm or classifier, and we're going to see that training it actually is a form of machine learning. So here at the conclusion to our 5-part series in graph algorithms, we're actually starting an introduction to machine learning, and then we'll do a simple quick demo. So we started off our series by pointing out that you can do analytics with graph algorithms, and as graph data and graph databases are becoming more and more popular and well-known and useful, they're being recognized as an important part of the portfolio that an organization is going to use to analyze its data, and data scientists should become familiar with them if they aren't already familiar. And you can think of the algorithms as tools, either as tools or as building blocks, because you build your larger program or your larger analysis out of them. They play you can end up using 1 or 2 or maybe 3 algorithms for your overall workflow. And there are different families of algorithms, and there are different particular ones within those families. And, of course, each one has its pluses and minuses. And what we've tried to do here in this series is to introduce the families to you, and then talk about some examples of particular ones within those families so that you get that knowledge, so you know how to choose, aha, I have this sort of situation, I should maybe use that algorithm. So we started off by looking at maybe, just for example, 4 possible types of questions you might have about your data, which you're trying to answer, and how they guide you towards a particular family of algorithm. First was which entity is most centrally located. Perhaps you are in logistics, and these days where I heard that 80% of Americans are now in a state where they're told to work at home, and 90% of school children are at home. So having things delivered to us is something we're very much dependent upon, and we're realizing how important that infrastructure is, that even when we give up all these other things, that still having certain basic essential things delivered to our general neighborhood, where then maybe we go a short distance to get it, is essential. And so doing that sort of analysis, thinking about what does it mean to be centrally located? What does it mean to be close? Are you more interested in betweenness centrality rather than closeness centrality? Those we covered in Graph Gurus number 27. Then we took a different look at a similar situation, which seems different on the surface, but actually is in a related category. How much influence does a particular entity have within a network? And that's relative influence, because it's influence on others. And it turns out that well-known PageRank algorithm is actually one of the algorithms that designed to answer that question. We then looked at similarity relationships. That was just the one we did previously in this series, which was Graph Gurus number 30. I think that was 3 or 4 weeks ago. And that's very common. That's a form of grouping where you're not grouping necessarily by location, but by their characteristics. And in particular, when you're looking at a graph, part of the characteristics is the pattern of connections. So not just the properties that you think of belonging just to that entity itself, but who you know, or who you interact with, or who you report to, or what store you shop at. Those type of relationships become important, and you can now think about that as a form of similarity. You're perhaps trying to identify people who have a family member who served in the military. So that's not something about themselves, but something about somebody who's related to them, or again, connections to experiences you've had, etc. And the last one we had on this example sheet was, what are the natural groupings within a graph? Finding communities, as we say, or components. And when we talked about that in Graph Gurus number 29, we talked about, you could think of a spectrum of different degrees of connection, where if all you care about is there's just one connection to somebody else in the group, that's fine. That's what we call a connected component. And that's a really foundational analysis you need, because a lot of these other algorithms assume that everything in your graph is connected. And if part of it is not connected, it's going to fall, it's not going to end up being part of the analysis, or it's going to confuse the results in some way. So sometimes a preparatory step is to run a connected component algorithm to isolate, okay, here is the majority of items in this one connected component, and I'm going to ignore the rest. Or at the other extreme, you can look as, are you connected to everybody else in the group? And then in the middle, are you connected to more people in the group than you are to people out of the group? And that's just a fuzzy way of saying, that's a relative definition of where do I put the boundaries. When you have those strict rules of just one connection or all connections, it's very simple to understand whether somebody is in or out. But when you have this relative boundary, more in than out, and the definition that's a realize moving that item itself changes the idea of what's in and out. So it itself is part of the decision of what is the boundary. So that's why it's interesting. And the Louvain algorithm is one of the algorithms that fits into that sense of finding that fuzzy boundary of feels more in than out. So I kind of just talked over these slides in part, so I'm not going to go over them in detail. Shortest path was another one. That was their very first one, and that's sort of the simplest thing that people often think of. It's often the one that people have heard about, and if they can name only one graph algorithm, sometimes that's it, shortest path. And maybe they even remember a way to calculate it from if they took computer science classes in school. So that's foundational. Anytime when we talk about traversing the graph, you are traveling paths and finding the shortest path, not just any path, but the shortest path or the least cost or cheapest path is sometimes important. We talked about centrality. I just talked about community detection, and I just talked about similarity. So today we are on part 5 of our series, classification. And what is classification? It sounds pretty obvious, but let's look at some examples of why, as somebody who is working for a business, whether a for-profit or nonprofit, you're working in some organization, it has needs. Why would you consider a classification algorithm? So here's one. So one of our, this actually relates to one of our customer cases of trying to detect good phone calls in the sense that this is the phone call you want to receive, you don't want it to be filtered out, versus a bad phone call, one that is some sort of spam or scam, and you would like that phone call to be flagged or filtered out by some AI system. So how is that AI system going to know? It's going to have to look at some characteristics. You've heard about blacklisting, where certain numbers are known to be bad. But how did it get to that? How did they find out it was bad? And how can we do a more predictive model with just a little bit of evidence to make as early as possible figure out that is the sort of annoying phone call that you want to filter out? Well, you do it by collecting these features of the calls and of the callers. And if you have enough historical data, and some of them have been labeled, as we say, where in that historical data, we found out in the past when somebody had, the phone call had these characteristics, then that person was likely a so-called prankster, where they're just maybe telling you some silly story, just trying to use up your time, trying to trick you into not trying to take your money. Just, it's more of a practical joke. And whereas these characteristics, that was a good call. There's just somebody, somebody who's an up and up salesperson. There's nothing wrong with salespersons. They got to do their job, and sometimes you want to hear from them. So you look at the number of one-directional calls was a distinguishing factor. So this person is calling a lot of people that never call them back. And I'll go, people who then maybe hang up, the people that this person calls, they end up having short calls, or the recipient actually ignores the call. So there's a high characteristic there versus a low number here, and so on. So what we had is we have 1, 2, 3, 4 different categories of callers. So that's what we mean by classification. We're trying to classify the calls into, in this case, 4 different groups. And we use this data or features of the calls and of the callers, and in fact, the whole community of callers, people who have called and have received calls in the past, which is then a giant network, is a giant network or graph of phone calls. We can use those characteristics to help train an AI system to make this classification. What type of phone call is this? here's some other use cases. Something that is very much on our minds. You're starting to feel some symptoms. Is it just a regular cold? Is it flu? Is it COVID-19? Or is it something else? And so here's a little decision tree, some yes and no questions. Do you have a fever? Yes. Are you experiencing shortness of breath? Yes, you may have COVID-19. And we've also heard there are cases of people who show almost no symptoms. And so that becomes tricky. So this is not trying to answer the question of who has COVID-19, but it's answering the question, I have some, symptoms like fever or coughing or sneezing. What is it? And that's even before you get a test. If you get a test, that can maybe just answer your question for you. But this is your first step when you're at home. So that sort of classification is on a lot of people's minds right now. And a completely different case, understanding natural language. And there are many applications here for written language or spoken language, doing conversation, where actually sometimes you call a customer service and it turns out you're not actually talking to a person, you're talking to a computer program. And how do they do that? And there are many things that go into that, but part of that is classifying what you say to them and trying to interpreting what you say to the program is in part classification. Was there a question there? Were you, and something that comes up in chat lines often or in reviews, is the person being sarcastic or not? Because when you're being sarcastic, what you actually mean is nearly the opposite of what you said. So that's one of the hardest things for those AI programs to figure out. And that's where that could get blended with sentiment analysis. And then, is there an expected response? Okay, I think I understand what the person said, but in this situation, socially, what am I supposed to say in response? And so that's there's a lot of AI going on there. The more you can break it down, and breaking down is classification. So the more you can break it down, the easier it's going to be. So here are two of the simplest types of classifiers. Rule-based. Here's a rule. If it walks like a duck and talks like a duck, then it's a duck. And then here's the same thing mapped out like a decision tree. So you ask the question, does it walk like a duck? Yes. Does it talk like a duck? Yes, it's a duck. So realize these are actually equivalent, except, and of course you could enrich in this to include other animals, other characteristics, etc. So, but where do those rules, or where does that tree structure come from? Did it come from some human's experience? So we call those like domain experts. Well, I know wildlife really well, and so through my years of experience or being taught by my mentors, these are the rules that we use. But we don't always have that benefit, and sometimes we're addressing new problems where the data is very complex and it's not easy to figure out that. So are there ways that you can have a computer or some program learn a classifier? And that's what we're going to talk about today. So the general problem of classifier induction, which is learning how to classify, it's based on looking at the data, right? So you have a set of so-called training instances where, again, you think just like in that phone, good, bad phone call case I talked about, you have instances, phone calls, and you have features, and then you have the final label. What type of item was this? So you know the classification categories, and you have some cases where you knew what it actually was. So again, like pictures of animals, and some of them say duck and some of them don't. So they're labeled. And you also have the features. You are told whether it walks like a duck, you're told whether it talks like a duck, etc. And through this, then using there are several different statistical methods you can use. So it depends on what type of classifier you're trying to build, and what type of data you have. Then there are different methods, but they're all in some form statistics to correlate the features to the labels, right? You're trying to find the strongest, which features are the most predictive. In fact, what happens with the decision tree is that the first question you ask has the most ability, the greatest ability to partition the data into, and in this case, because it's a binary yes or no question, the purpose of this question is to separate things into two halves and to do the best possible separation. I arbitrarily put these questions in that order, but if you were trying to make a best possible decision tree, it would actually matter which question you ask first. So that's the general problem and the general form of classifiers. And as I said, this is one type of supervised machine learning. Supervised means we have some training data with preferred answers available, and we're going to use that to train the system. That's the supervised machine learning. So I said the one we're going to focus on today, and we're going to show how we're going to relate this to a graph, of course, because we're talking about graph algorithms and graph analytics, is the K nearest neighbor classifier, or it's abbreviated KNN. Excuse me. And the general concept is we're trying to predict an entity's class or its classification by looking at the classes of the nearest other entities. So in this figure, I'm assuming this is the entity you're interested in, the one in the center, and you look at the ones that are nearby, and we've mapped them out physically. So obviously that red one is the closest. And so the assumption is that distance is predictive. And again, so this is where you have to make sure that the technique you're deciding to use, say KNN, is in fact a fit for your situation. Why should closeness help you predict something's class? Well, it depends on what you mean by distance. If you mean physical distance, then it's often not true that just being close to something, if I stand next to a duck, it doesn't make me a duck. It's true that maybe certain animals gather in herds, but again, that's not a good enough description. But if what we mean by close is we're actually going to measure similarity, and where we're placing these things is not their physical location, but we're placing them by their similarity to one another, then this starts to make sense. So then the only question we have to answer is this K. Why is there a K here? K is a variable. It's an integer. It's the count of how many neighbors should you consider. You could consider a radius, like everything within a certain radius, or you could say, well, count the 5 nearest neighbors, 1, 2, 3, 4, 5. And that's what it typically does mean. So you'd say, I want to use, KNN where K equals 5. That would say, look at the 5 nearest neighbors. In this case, okay, 3 of them are this, beige, yellow, and one's red, and one is white, or actually unlabeled. I meant that to be unlabeled. So looks like yellow wins. So think about it this way. So here's that same little figure, and I've copied them out according to distance, closest to farthest. So again, like I said, I think this is, well, I changed some of the colors because I wanted to make sure it worked out for my example. So that's the closest, that's next closest, so that the first 2 are yellow, that then unlabeled, then a red, then a red, then another red, then an unlabeled, a yellow, an unlabeled, looks like that red, yellow, and yellow. So that's how I got that order. So then you can just say, well, for different values of k, if k is 2, I just look at the first two. They're both yellow, so the prediction is I must be yellow because the people most similar to me are yellow. If you extend it one more, you got yellow plus an unlabeled still means yellow, and so on. So if you go up to say 9, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, then you see that you ended up with 3 of each. And so that means actually you can't really make a prediction. You might have some method for a tiebreaker, but in this case, we're kind of stuck. If you go over to 10, then I have this red one. And so that tips the scales in favor of red. So that's the concept of what we're doing, how you look at the nearest ones in terms of similarity, and the majority class wins. So again, given that you have some sort of distance or similarity measure, so notice these are just inverse functions of one another, right? We say similarity is here where you're thinking in terms of property or some characteristic, and so when it's very similar, we say it's close, and when it's not similar, we say it's distant. So these are just inverses of one another. You don't have to have any intelligence to the system other than just that measure of how do I measure similarity. I show you two animals. What characteristics are you going to use to measure the similarity of two animals? So there has to be some sort of guidelines or some rules that you follow. But assuming that you have that function, that's it. You just need some value of k. So the item you want to classify, somebody tells you what value of k to use. You compute the distances, so you figure out who's similar, and then just count how many items up to k, and there's your prediction. So it's quite straightforward. So there's no machine learning there. And you could apply it though. So the machine learning comes in, excuse me, that should be an ML, ML task. What is the best value of k? You know, I saw here before, I showed you the results for all 2 through 12, and you get different answers. And so how do I decide what's the best value of k? So that's one task for machine learning. The other is you could use it to actually optimize or find the so-called best distance or similarity function. I said that's a very important. That's fundamental to how you're going to get your answer. And we haven't said where that comes from. And maybe finding the right distance function is what you need to do to sort of learn your optimal system. So that's something else that could be done. But we're not going to talk about that today. We'll maybe in one of our future discussions that are focused more on machine learning, we'll talk about that. So everything I've done so far hasn't really had anything to do with graphs. So where is the graph part? You may have studied KNN before in a non-graph context. You didn't need a graph. So how would it apply to a graph? So one way, the way that we'll be doing here today is it's about the distance or similarity function. If you were here for my previous webinar, I talked about similarity functions in the context of a graph. So we introduced 3 of them. We introduced cosine neighborhood similarity, Jacquard neighborhood similarity, and simrank. So we're going to use cosine. We can use cosine neighborhood similarity, but it would be easy to swap it out with Jacquard. And if you remember, or those of you that weren't with us last time, I'll just say it very quickly, that what we're doing is we're looking at who the neighbors are of A. If you're trying to compare A with B, we'll look at who are the neighboring vertices for A, who are the neighboring vertices for B, and comparing those two sets. And if it's cosine similarity, then we need some numerical measure. So if there are edge weights, then we use those weights. And there's a formula you use, and throwing in those edge weights, and again, the identities of who you match with, those can determine the similarity score. And then one more part I'm going to talk about before we kind of wrap it up and get to our demonstration example is the important step of cross-validation. So whenever you're training a model with supervised learning, you first train it and then you validate it or check the accuracy of your model. So your training process gives you a proposed model, and then you go back and see how well does that model work, and why do you actually have to do it in 2 steps? You do it in 2 steps because you have your training data. Again, your training data has labels. That's the key thing in supervised learning. You have these examples where the target result is known. And so in this case, since we're doing classification, it means the classifications of the items in your training data are known. But really what matters is how good do they predict? So what you do is you kind of mask off the answers for some of them, and you train as though you didn't know that, and then you go back and check and see if did you actually predict what is the real answer. So there are 2 common techniques, and one is just sort of an extreme of the other. Maybe the most common is I called it n-fold cross-validation. It's usually called k-fold cross-validation, but I didn't want to confuse this k with the k and n, so I called it n. That is, you split up your data into n equal size groups. So if n is 5, I have 5 groups. You take 4 of them together, 4/5 of the data, and use that for training. So whatever your technique is, it depends on the algorithm you're using, whatever technique. That produces a model, which then, if you have a new item, it's supposed to tell you what it thinks the classification is. And you run that model on the remaining section of the data. And then you repeat that. So in this case, I picked the last group as the validation set. You repeat it with that one as validation, or that one, or that one, or that one. So you rotate all the possible combinations of which one is the validation set and use all the others for training. And there's another technique similar called leave out one, where you just take one item out and train everything else, and then use the model to try and predict the classification of that one. And so I think I kind of gave you everything you need to know to understand the outline of how the classification algorithm in our algorithm library works. So as I said, we have one for k nearest neighbor. It uses cosine neighborhood similarity. And the CV is abbreviation for cross-validation. So given a either fully or partially labeled graph, so that means this is my training data, and it's sort of a unique characteristic that we don't even require that it be fully labeled. You want enough, and it'd be nice if more than half the data were labeled. It'd be nice if it was all labeled, but it doesn't all have to be. Some similarity measure, as I said, we have to be able to measure similarity or distance so we can say which ones are nearest, and we're going to use cosine neighborhood similarity. And then the user gives a range of k values that he or she wants to consider. You can consider all the way up to the size of your graph. You can, if you want. You usually want to keep it more modest. And it doesn't matter that much. It's just the bigger a range you pick, the longer it's going to take to train, because it's trying more cases. So a range of k values to consider, the similarity measure, and the graph itself. What it does when you run the trainer and cross-validator, it's going to look for each value of k. So it's going to pick one value of k within your range. And then it's going to go through the graph, and it's doing a leave out one validation. So for each item q in the graph, that's the one it's leaving out, predict Q's label by looking at the classes of the K closest entities, and then check if that prediction was actually right, and sum up over the whole set of all the different Qs, because you're going to do it for each item in the graph, and then you're going to calculate the total number of how many correct predictions did you make. Or you can also think of that as a percentage, right? If you had 100 items and you were right 82 times, then you were right 82% of the time. And you did that for one value of K. Now do the same thing for a different value of K. Do it for each value of K in your range. Select now that you have all these accuracy scores for different values of K, just pick the one that produced the highest accuracy score. Ta-da. So now we're going to go to our demo. And the data set I'm going to use, it's pretty small because we just want to show you the concept. This is based on the same data set that we have in our documentation with the graph algorithm library. So the graph algorithms themselves are on GitHub. And then along with our regular product documentation, we have one section that's for the graph algorithm library. So when we describe the algorithm in our documentation, we've got this, which has, these are movies, which came out in 2017 or 2018. These are genres, which I added, and these are 6 hypothetical movie reviewers. And so they've got names, and they also have labels, you see. And that's the part where I said, so this is our training data because we do know the labels. And this is just artificial data, so the label doesn't really mean anything, but these 3 are A and these 3 are B. And you see the different, these weights are the scores they gave to the movie when they reviewed it. But I think, yeah, and that is part of, if you remember, the edge weight is part of the cosine algorithm. So what we're trying to do is trying to see, when we say which reviewer is most similar to another, it's going to have to do with not only how many movies did you both see. So you can see Kevin and Neil. Neil reviewed 4 movies. Kevin reviewed 3, and they overlap on 2 of them. Movie 2 called Searching and movie 7 called Crazy Rich Asians. I think that's, yeah. Okay, so that's the data, and let me switch to, so this is an instance of TigerGraph Cloud. What I just click? Try to make this a little bigger. The graph schema for this is, again, just 3 types of entities: a reviewer, a film, and a genre. There's the graph. Now, one thing you may not have known about Graph Studio, even if you've used it before, is that, we have these 2 different ways to explore the data, either this interactive ad hoc panel or this one for queries, where this is where you would author your queries. So here I have 4 of them related to KNN. Let's see if I can make this text a little bit bigger. 4 of them related to KNN. Single SS, the SS suffix means single source. That means you pick one vertex as the single source, and then it's going to give you a prediction for every, let's see. So it's going to do a similarity with every other one, or actually every value of K. We'll run it and you'll see. All is where I think it tries each possible vertex. Remember, I said in cross validation, we did the leave out one, so it wants to do all one. And this is the cross validation one, where it's doing both the training and the validating. What I was going to say is, you may not have known, you can actually run the algorithms from here. So this last option here is if a algorithm has already been installed on the previous panel, then you can just pick one here. And so this is the single source one. I pick a reviewer 0, and I have to pick a value of k, let's say 3. And so the thing is, it's designed to like show you the output. Excuse me. Now it didn't actually show me the result I wanted. So that's why it is in fact better to run it over here, because here I'll actually see my result better. Let's see, query, single source, reviewer 0, 3, and run. Okay, so it predicted A. Now, is that correct? I can just, if you remember from the data, there are 6 reviewers. So the first 3, 0, 1, and 2 are A, and the last 3 are B. So this is correct because let's just throw in another value very quickly. That also predicted A. Let's see if I do 4. And let's see if I jump to the other end, if it switches the answer to B. No prediction. Remember, sometimes it was tied, and so then it could not actually make a prediction. Or maybe there's just, there's no connections. No, there's not enough data. Ooh. Oh, there is no 6, sorry, because it only goes up to 5. So I can actually, because the graph is so small, we can run the full cross-validation in just a fraction of a second. So what it wants is, remember, the range of k values you want. So let's go from 2 up to 6. And it's done. And remember, it calculates a score, an accuracy score. And so it says if k is, it didn't show you the k values. I could probably edit this really quickly, but that represents k 2, 3, 4, 5, and 6. And you see when k is 2, it was right half of the time. And when was k 3, 4, 5, or 6, it was only correct a third of the time. Remember, there are 6 reviewers. So that means 3 out of 6, and that means 2 out of 6. So obviously the best value is 2. And I want to run one more case to show you just, I think this all, it sort of breaks down a little bit more clearly what it's doing. So if the value is, if the value is 2, so this gives a bit more informative output. So, and it goes through all 6 vertices. And so it says for vertex 2, it predicted B, but the correct answer is A. For 4, it predicted A, but the correct answer is B. Wrong. 3, predicted B, actual B. A, no prediction, B, and A. So that's why we saw that, 3, yeah. Remember, this is for k equals 2. So it in fact was correct 3 out of 6 times, right? 1, 2, and that last one, 3. And if I were to change the value to anything else, like say 4, and then you say, okay, wrong, correct, correct, oh, correct, wrong, wrong. So this looks like 50% correct. So why did it say before that there's only a third? I will have to take a closer look at that later. But, and let's see if we can, if we go back to the graph picture. So here's the graph picture. So again, what it's doing if we ask it for 0, make a prediction, and then for a given value of k, what it's going to do is it's going to measure a similarity score, a cosine neighborhood similarity score between 0 and each of the others. So there are going to be 5 similarity scores, and there are going to be 5 distances or similarities to each of these others. And because I picked k equals 3, it's going to take the 3 that are closest, that have the lowest, 3 with the highest similarity scores. In this case, for similarity, higher is better. So it's going to calculate scores for all 5 and then take the 3 that are highest, those, and then it's going to look at the classes of those 3. And because that's an odd number, there's a good chance that either A or B will win. So actually, if you pick k as an even number, then you have a possibility of getting a tie. So that's why maybe it's better to pick an odd value for k. And that is basically that. So, you know, over the course of this series, we've both introduced the algorithms to you, and we've showed you how you can use TigerGraph, Graph Studio, and the GSQL Graph Algorithm Library. I could show you the KNN code if you'd like, but the thing is, it's just written in regular GSQL. If you become a little bit familiar and a little bit proficient with GSQL, you can go in there and edit the algorithms to customize. I find that I often want to customize the output because it works. It is doing what it's supposed to do. The algorithms, the versions that we put in the library, we tend to put kind of minimal output because people don't want extra stuff. But sometimes particularly when I'm doing these demos, I want the output to be more descriptive, so I will edit them for that purpose. But you may have for any reason that you have. And those algorithms, you can either run them directly through the interactive GSQL interface, or if you want to put it embedded in a program, each one also has a RESTful endpoint. They do run directly in the database. We're not exporting the data, so that can be very useful when you're running on a large amount of data. The not having to export the data can save you a lot of time and resource. You can actually update the graph itself with the algorithm results. So that's another advantage of being running in database, that you can immediately, during the course or immediately after running your algorithm, you can make a decision to update the graph itself. We already talked about the ability to modify them, and you're running on the TigerGraph platform, which is massively parallel processing, is distributed graphs. If you have a very large amount of data, you can distribute it across multiple machines. So it really has a lot of performance advantages in that case. So to sum it up, in this series, we sought to introduce you to graph algorithms, which are increasingly important tool for data scientists to use. We talked today about classification algorithms to help you bridge the gap to machine learning. You know, it's sort of fitting that this comes at the end of our series on graph algorithms. While there are even more, 5 was not the, you know, magic number. You could come up with another category of algorithms, which we have not done. This is more of an introductory series. But even in doing so, we thought by now you've sort of built up enough understanding that it makes sense to kind of introduce you to machine learning. And we looked in particular at the k-nearest neighbor algorithm, which predicts a classification by looking at the classes of these similar or nearby items. And the training question here is picking the correct value of k. So we would love to have you take a look at the library. You can try TigerGraph for free, either on the cloud or do a download for free. And with that, we will open it up to questions.
Thanks, Victor. That was fantastic. I learned a lot, and I especially enjoyed your explanation of the KNN classification. That was very thorough, very insightful. Let's see, questions. We have a few so far. I would encourage everybody in the audience, if you haven't submitted a question, you can do so by clicking on the Q&A tab there and submitting a question to us. Here's a question. I learned KNN before, and as you said, it doesn't necessarily need to have a graph. Are there guidelines for when it's a good fit for a graph?
That's a great question. So I had to find an example case to use for this presentation. And the one that we use in our documentation is a fit because it's a so-called bipartite graph. I actually showed 3 types of entities. I had the reviewers, the persons, the movies, and the genre. Though you may have noticed I didn't actually use the genre. So I was only using 2 types. So when you have 2 types and the relationship links one to the other, so people review movies, then that turns out to be a good fit because that is also the fit for our neighborhood similarity algorithms. The cosine, notice we don't, if we're giving the full name, we don't just say cosine similarity, we say cosine neighborhood similarity because we're putting a graph spin on it where what the parameters or the properties we're looking at is the membership and the weights to connect to the neighborhood, which is a graph characteristic. So if you have a bipartite graph where you have 2 main types of entities and they connect to one another, that would be a good fit for this KNN.
Fantastic. Another question is, do you plan to add other classification algorithms?
Yes, we're always expanding our library. Both for my previous presentation on similarity, I developed one. Well, I wrote one out. I didn't create it, but I wrote one out, SimRank. And for another presentation, I did, which was not for this series, but elsewhere. I did a maximum flow algorithm, which is another well-known graph algorithm. And so we'll be adding those. So we're always adding them. They just need to go through some little quality assurance before we're ready to publish my sort of handwritten ones. But and so, as I said, classification kind of overlaps with machine learning in some cases. So we're also expanding our offerings on machine learning. So those will kind of go hand in hand. So stay tuned, and because can sign up for our developer newsletter, or just we have a community. I'm wondering if it's listed here on these slides. We have developer office hours. We have a developer forum. So there are ways to stay informed about what the things that we're developing.
Cool. Next question is the KNN algorithm ideal for identity resolution use cases for merging and matching customers?
That's a very good question. I don't know that I would say it's ideal, but here's how I would think about it. So identity resolution is when you have 2 or more identities, usually persons. Let's use the example of people, for example. And they have so-called digital or cyber existence. 3 different entities for which they are listed in some database or data set. And the question is, do they in fact represent the same real person? Like, for example, I have multiple different email addresses. There's my work one, and I have multiple personal ones. I'm still the same person. And the question is, which other company out there has managed to use their intelligence to link them to figure out I'm actually the same person? That's the entity or identity resolution problem. So would KNN help for this? Yes, if you, again, I said it comes down to the similarity measure you use. And that is sort of like the $64,000 question with entity resolution is, what factors am I using to determine, for me to judge that these persons are the same, or so they're so similar that I think it's just in fact the same. So this is taking it to the extreme where you're saying they're so similar, I think it's the same person. So yes, it could be used for that.
Mm-hmm. Okay, interesting. Next question. Is that code/project available for us to review?
Yeah, the KNN algorithm is already in our graph algorithm library. I did not write it for this presentation. It was already there. It's been there for some months. So you can go to our GSQL graph algorithm repository on GitHub and take a look at it right now.
And the last question we have, are you planning to add more machine learning tools in general?
Yeah, I think I answered that a little bit earlier, because yes, we're getting a lot of questions from our users are very much interested in machine learning. And we are, we want to deliver value to our customers. So we have a small team, and we're building a larger team to help, and we're working with partners to help produce more machine learning related tools for our customers to use. Okay,
cool. That appears to be all of the questions we have. And given the time, I suggest we move forward and wrap up the presentation. Victor already mentioned the developer forum. You can join that if you have more questions. And I highly recommend our developer office hours. That's something we do every Thursday at 11 a.m. Pacific time, Pacific Daylight Time, Daylight Savings Time. And it's an opportunity for you to have a live sort of Q&A interaction with one of our subject matter experts. I think that typically lasts for about an hour or so. If there are sufficient people on it, we keep that open for about an hour. Next slide, Victor. And here are some additional resources. I also recommend that you check out Tigergraph Cloud. This is a sort of a low barrier or no barrier to entry type of way for you to get exposure to using graph database. You can sign up for Tigergraph Cloud in just about 30 seconds or so. It's a very streamlined process, and within 5 or 6 minutes you'll have an account. We have pre-populated Tigergraph Cloud with almost 20 starter kits. Indeed, it might even be more than 20 starter kits now. And the purpose of those starter kits is to make it easy for you to pick a starter kit that's relevant to your use case. And then there's already schema within that graph, and there's some sample data, and both the schema and the data can be modified if you want. But if you don't want to modify either, it's a quick way for you to get going and begin to roll up your sleeves, as it were, and get experience with Tigergraph Cloud. There's a free tier, free in perpetuity. And if you want to have more than one solution, you can provide a credit card, and we give you $25 of credit, which is about 10 hours of time to get experience with Tigergraph Cloud. So really, there's no reason for you not to sign up for Tigergraph Cloud if you haven't done so already. Additionally, there are other resources listed here on this slide, which I won't go through in any detail. Next slide, Victor. I do, however, want to draw everyone's attention to our webinar next week. And also I want to reiterate that we do these webinars every week at the same time, 11 o'clock Pacific time, 2 o'clock Eastern time. And so just check your calendar each Wednesday if you want to have an opportunity to learn from our subject matter experts. Next week's webinar specifically is on GSQL writing best practices. This is part 2 in a series. It might become a series of 3 or possibly 5. We don't quite know yet, but this is part 2 in our series. and it's presented by Xingyu Chang, who is our Director of Customer Solutions, one of the authors or creators or developers of GSQL. So by attending this webinar, you're hearing from the very best, and I think it's well worth your time to register and attend. Again, next Wednesday, 11 o'clock Pacific. And yep. That brings us to the end of this webinar, and it brings us to the end of this series of 5. I hope you'll agree with me that this has been a very interesting webinar. And for those of you who have listened to the entire 5-part series, a very, very well worthwhile experience. And it certainly has expanded my knowledge of graph algorithms. You can review parts 1 through 4 on our website. And as I mentioned at the top, we'll shortly have this episode, this webinar on our website too. And so you could, while you're self-isolating, continue your learning by revisiting parts 1 through 5. I think you'll find that very worthwhile. We know you're very busy, and we appreciate you spending the last hour with us. We hope you found it to be informative. We look forward to seeing you at another Graph Gurus webinar in the future. Thank you, and stay safe.
Thank you, everyone.